We took some professional hits because our supervisors told us to stop, and we kept talking to other people, but we knew it was important for the country, and we just kept going. As you get below about 90 nanometers, your options, your suppliers get much less in the world, to only a handful. Those handful of companies were largely manufacturing overseas. And so as we saw the need in national security systems becoming greater in terms of processing power, particularly for AI, we couldn't source those components onshore. It took 4 years to convince Pentagon leadership, congressional leadership that we had to do something about it. That was a very difficult time and a difficult conversation to say, these are important for national security and economic prosperity, and we need to do something big to bring those companies back and that production back to the US.
More often than not, the programs, at least on the DoD side, don't really help to influence manufacturing. They point back to the technologists and say, hey, that's your problem, man, not my problem, right? How did you break down that barrier? That's a tough one. That's a tough nut to crack.
This was the biggest change in industrial policy, I think, since World War II.
Hey, Greg, thanks a bunch for joining us here on Micro Journeys. It was nice and convenient to catch you at the HEART conference. Pretty good gathering here. I mean, what, 400 or 500 people, something like that?
Yeah. I don't know if it's the largest gathering yet for HEART, but it's pretty big. It's been growing over the last 10 years for sure.
Absolutely. Oh, this is my first time here. And seeing the entire, community, how close-knit it is, being able to just, interact with everyone in one setting is just phenomenal. So yeah, no, welcome to the podcast here. And the goal here is for us to kind of get to know you as the person. You've made such an impact to many different portions of technology, whether it be microelectronics, fusion. You've done a lot of stuff with the Air Force, with the Department of Energy, impacting even departments that are kind of non-classical with the Department of Commerce, right? I mean, some of the stuff that you did was foundational for chips-related programs and, different types of things that have came out from the White House. So it's exciting to hear kind of how you've, started out almost grassroots, right? And then growing into an area that was breaking down not only a lot of, personal barriers as it relates to different opportunities and the such, but not kind of the classic role that your family has gone through. So you grew up in Wisconsin, no?
Wisconsin, yeah. Yep. On a small dairy farm. Yeah. It was fun. It was fun. Hard work, but taught me a lot.
Yeah, we were talking yesterday about ice fishing, right? And something that's super foreign to me, you were telling me about, you can drive out to the ice and just hunker down with your car, go into like a little shed, put your pole down and just kind of hang out for a few hours, right?
Yeah. Ice fishing, snowmobiling. That's about it in the wintertime. Yeah. Try to keep your car warm and plugged in those cold nights, and hopefully it starts in the morning. So
your family's pretty much involved with a lot of farming related stuff, right? You want to go into that a little bit?
Yeah, I grew up on a dairy farm, small family dairy farm. And it's not just my family. It's all my aunts, uncles, and cousins on both sides of my family, mother and father side, all farmers. And I was kind of the one that, escaped, did something different. I liked farming, but I didn't really feel a calling. But the thing that I took away from that was the joy in producing something from nothing and giving something that people need, which is food to live. And so long term, I've been thinking about that and we'll get into it. As I was in the Air Force, I was mostly buying things that other people produced. But then when I thought about transitioning out of the military, I really wanted to make the things that were important for national security systems, energy systems, and other industries.
How was the takeaway going from a technology kind of pathway in life from what was historically done? Was it something that was, really encouraged? Was it not? I mean, how did you kind of bore into that area?
I was thinking about that the other day. I don't actually know how I got into engineering. I was always good in school. And I was always interested in math and science. I had a couple of great teachers, like a lot of people. I had a great physics teacher in high school that kind of really opened my eyes to science and how interesting it is. But to be honest, I knew nothing about engineering or any of the science degrees. My family, they encouraged me to do what I wanted to do, but they told me you can go to any school you want. You just have to pay for it all yourself. And I kind of took the time to research schools and apply. looked at the academies, Air Force and West Point, ended up getting a ROTC scholarship, which helped me pay for the school that I went to.
Oh, outstanding. So you went to the academy then, right?
No, I ended up going to Rose-Hulman Institute of Technology, which is an all science and engineering undergraduate school in Indiana. Great school. I learned a lot of great things out of there. I mean, initially, the interest in the military came from like a longing to give back. I've always had this service-oriented attitude that I wanted to give something big back to the world, to the country and to the world. And when I was 17, I joined the Army National Guard. I had to get my parents' permission. And then as I was doing training for a year in my senior year of high school, waiting to go to basic training, that's when I transitioned into the ROTC program and then went to the Air Force ROTC. Went through the Air Force ROTC program in college.
Okay, so then after you finished up college, it allowed you to just continue on with the Air Force. It gave you the opportunity to be a part of the Air Force, then, right?
Yeah, I was commissioned a second lieutenant. We have a 4-year commitment after we get commissioned, and my thought then was, I'll do 4 years and I'll get out and figure out what to do next with my life. But I always told myself, if I loved my job and I was making a positive impact, I'll stay in. And I just stayed in 22 years. So 22 years later, it was a great ride. I've done a lot of amazing things, great bosses. I was really fortunate.
So what did young Greg start out with in the Air Force, right? Because we covered a lot of, these kinds of latter portions of your career of what you got involved in. What did young Greg get involved in at the beginning?
My first job was at Hanscom Air Force Base in Boston. I led a small team looking at flight software and making sure that it didn't have the errors that would cause accidents, for instance. So I worked with FAA people, looked through thousands of lines of code, make sure that the testing, the configuration management, quality management were all in place to ensure that there weren't any errors. It was a fantastic job. I learned a lot. I didn't feel the calling for it, but I still have a lot of colleagues in that area, and I really look up to them. But then after that, I went to the Air Force Institute of Technology to get a master's degree. I wanted to get something other than EE. That was actually my undergrad, and economics. So I've always had this dual interest in engineering and finance/economics. But the economics part didn't really play a part in the military life. Until you become a program manager. So I went to the Air Force Institute of Technology, got a master's degree in systems engineering, focusing on nuclear engineering and space systems. So that allowed me to look at other areas outside of the EE curriculum.
Did you touch on any kind of nuclear-related stuff prior to that, or was it just an interest area?
Just an interest area, yeah. And the science is amazing, and I really love particle physics. So that's kind of changed my life forever.
You got your PhD there, correct?
Mm-hmm. Yeah, I went after the master's. I went to the Defense Threat Reduction Agency, then went back to AFIT for a PhD in nuclear engineering.
Kind of two sets of experiences here. You have, what you were doing with, ensuring that, planes don't crash into each other with the FAA and the such, and then now taking a pivot over into, the nuclear realm of things, right? So after you finish up at AFIT, how did you get involved with like microelectronics? I know that was an area where we met each other. Kind of curious how a nuclear background gets you pulled into that area.
After AFIT, I went to the Department of Energy, ran a $200 million a year office there in the R&D space. Part of my job was to lead an analysis of alternatives on where to source future electronics needs for national security. And that got me into the electronics world, and along with my radiation effects background. And so with that, that's how we met. And that summer, I think I saw like 15 fabs in the US, and I was able to really look at the infrastructure and the lack of production that we had onshore for critical components.
So let's take a step back. So you're saying this analysis of alternatives. Paint the landscape here, right? I mean, at the time, what I remember is that we were at a kind of an inflection point in the United States where manufacturing was being questioned as it relates to where we were going to source our components and the such. Can you kind of give a little background on, spearheaded this AOA or this analysis of alternatives?
As the years go on, the feature sizes get smaller and it gets much more expensive to produce. And what you see in industry is that as you get below about 90 nanometers, your options, your suppliers get much less in the world, to only a handful. And those handful of companies were largely manufacturing overseas. And so as we saw the need in national security systems becoming greater in terms of processing power, particularly for AI, and we saw this kind of AI revolution coming in the near future, we knew we'd need that increased processing power, but we couldn't source those components onshore. In particular, Taiwan is a big place where they're manufactured. China also to a great extent now, although back then it was still kind of increasing, and it wasn't on everybody's radar that it was such a challenge to get those companies to.
So this was pre-big fund, right, over in China. So, but I mean, kind of looking at the political dynamics of the world today, looking at that problem when you did, I mean, it was such an early snapshot of where we're at today, right? Taiwan, what manufacturing is at 98%, I think, of all electronics in the logic regime. And it's not like tensions aren't high in that part of the world, right? So the landscape right now is we're looking at 90 nanometers as being kind of the like I said earlier, the inflection point for technologies. And it's also a interesting piece because it's a bridge, right, from where state of the practice related technologies were at the time, your 200 millimeter wafers, and then bridging into now kind of this new paradigm, 300 millimeter wafers, where most copper back-end technologies are manufactured and the such. So it's kind of a decision point. The United States needs to make sure, are we really going to be playing in this space or are we not? And how are we going to do that, right?
Yeah. And it took 4 years to convince Pentagon leadership, congressional leadership that we had to do something about it. And that was a very difficult time and a difficult conversation to say, these are important for national security and economic prosperity, and we need to do something big to bring those companies back and that production back to the U.S. We had a lot of tough discussions where senior leaders would ask, what's the requirement? And if you're in the military, the requirement, what that means is a validated requirement through the JSIDS process, which takes a very long time to do. And it's right before a program starts. And so if you wait until addressing it to when a program starts, you're too late because of the timeline to actually build a new fab and get, the line qualified.
Those don't really align with DoD acquisition timeline.
No, so what we needed to do was look at it more, future oriented, not in the past or what's currently out on the market. And that was a huge inflection point for industrial policy. I mean, that's in my career, I think that's probably the biggest source of pride that I have, that I was able to do myself and one other person in DC, really pushing through a lot of roadblocks. We took some professional hits because our supervisors told us to stop, and we kept talking to other people, but we knew it was important for the country, and we just kept going. And so it took 4 years. In that time, we also talked to Intel Corporation and really got them back involved with the U.S. government, first time in 20 years.
Yeah, it was a big pivot. I remember there was a number of conferences that took place, both unclass and class, and classified. And it was interesting because their center stage was Intel Corporation. Prior to, they were just not interested in playing with the government. They had their own standard parts. They were out there very comfortable in manufacturing those. And it was the first time that they'd actually entertained the idea of, well, what if we actually manufacture things in a pure play model? What if we actually manufacture things for the government? What if we actually do this in a protected ecosystem? And now it just opens up a lot more doors from a manufacturing perspective, right?
Yeah, and I think the story is not always told of how we got there. That was a lot of trust building that we did through multiple programs, a lot of conversations, and trust on both sides that this partnership was going to grow. It was tough. It was long. But after 4 years, like I said, we could really see the buy-in at the senior leader level, and then another 4 years to pass the CHIPS Act.
Yeah, it was interesting because you say from the program perspective, more often than not, the programs, at least on the DoD side, don't really help to influence manufacturing. They point back to the technologists and say, hey, that's your problem, man, not my problem, right? How did you break down that, barrier? That's a tough one. That's a tough nut to crack.
As we go forward, I really think we've been we've been basing our requirements largely on intelligence reports over the last 20 years. And that's worked for the fight that we've been in, where we're not against a near peer technologically advanced adversary. Going forward, we need to both look at the intelligence reports and we need to look at where technology is going wherever it's, whatever country is actually developing it, because it can be adopted by any country, right? You can have a breakthrough in Australia and China takes advantage of it, or we take advantage of it. And so you have to look at the open literature. You have to involve the technologists and the engineers and the scientists to see really what's the forecast over the next 10 to 20 years? What are the probabilities of those forecasts coming to fruition? And then how do you influence the requirements in the program to take advantage of that? Because if you wait, it takes 10 years to get a program out the door. Minimum, right? So if you're basing it off of intelligence reports that are only really, they're only good into a certain amount of the future, they start to get very hazy. You need to bring in another data source, which is where the technology is progressing.
Interesting. Yeah. And a lot of the discussions that I've had with the co-coms and the such, you get a lot of this, right? You get, hey, I have a problem that's, I have to address in 6 months, right? So I have to be able to execute in that 6-month time period. That's the technologist problem. The technologists are asking the question, hey, we really need to know what your guys' mission operations are so we can go ahead and design out for those 10, 15, whatever the procurement cycle looks like, type of timelines, so we can go ahead and integrate in the appropriate stuff. And then the third leg of the stool here is the, the fabricators, all of the semiconductor ecosystem, right? That are saying, look, we don't operate in any of those timelines. We operate in, 18-month timelines. And then if that doesn't happen from, a demand perspective, then we're going to sunset things. So now you're juggling all of these different pieces as you're trying to say, look, domestically, this makes sense. Not only for us to manufacture stuff, but to really take a serious look at how we're engaging with companies, both those that are here and those that could potentially be here to buy down our risk, right? And it's a bigger problem than just the DoD. I mean, this problem spans the entire critical infrastructure of the United States, right? What is there, like 16 sectors or something like that? A pretty large lift. So when you're developing this kind of analysis of alternatives, right? What's kind of the pathway for something like this? You get an answer, right? And with an answer like this, it influences all these different pieces. You're talking about commerce. You're talking about this being sponsored by the Department of Energy. I guess where are all the touch points as it relates to something as transformational as a document like this?
There are a lot of stakeholders, like you mentioned, Department of Energy, Department of Defense, DOC, state, bringing in like ITAR restrictions. You have to have a very collaborative attitude. It's not just where the money's coming from and where the requirements are coming from a system standpoint. It's also, who's going to write the policy and how do those policies directly or indirectly affect what you want to do?
And it's interesting because you're one of the few people that I know that got to experience both the technological challenges and the political challenges, right? Which I think helped to springboard you into, the second portion of your career, right? Understanding how to balance both of those at the same time, ensuring that the buckets don't overfill on both sides and you're able to continue pressing forward. So after you finished up at the with this AOA study, right? That goes and it gets a life of its own, helps for foundational pieces like the CHIPS initiative, like we described. And you're seeing, announcements even earlier this year where companies like TSMC investing, hundreds of billions of dollars in domestic manufacturing. And you look at kind of the breadcrumbs on where that goes all the way back. And if there's not evaluations that are looking at things like, hey, where do we source our electronics? Maybe that collaboration never happens. Maybe that discussion never happens. Maybe there's no Arizona site that is there. So it's an interesting, impact that this has had across the United and worldwide, not even just the United States.
And it's more than just the fabs down to the workforce. Just highlighting the CHIPS Act as a national imperative pushed a lot of colleges, tech colleges, high schools to adopt programs pushing curriculum in that direction. So there's broad reaching, along with all the networking that happens, like you mentioned. It's not just money going out the door. It's the whole ecosystem that's being rebuilt.
Do you think it's going to be able to absorb the ecosystem? I mean, because there's such big gaps in all of these different areas, right? Everything from resources to rare earths to workforce. How do you think the absorption is going to be with such a paradigm shift in the United States?
It's going to be challenging, for sure. I mean, this was the biggest change in industrial policy, I think, since World War II. I mean, we are now actively investing in critical industries to a very large degree, and it isn't going to stop. I think the breakthrough from a political standpoint that we made was convincing both sides of the aisle that it had to be done. On one side, we don't want to interfere. The government doesn't want to interfere in the private markets. On the other hand, we also don't want to subsidize large CEO paychecks. Like, that's not something the government, that's at the top of their priority list. But at the end of the day, we had to do it. And I think the great thing about this nation is, to your point, when we have to do something, we just get to it and get it done.
It's very rare to have both sides of the aisle. I mean, that's how the CHIPS initiative was passed, right?
Yep, absolutely. Yeah.
And so it's interesting. You see the spectrum of awards that comes out from something like this. You have Minnesota getting awards. You have locations over in Texas. You have locations over in New York. I mean, it was not a single state. So that bipartisan support, I think, really allowed a lot of these different states to step up to the plate and say, look, not only are we going to support this by signing off on this bill, we're also going to create incentive packages to bring it to our home state, bringing in all different types of job opportunities, but also an ecosystem that can build around some of these towns and cities that may not necessarily have that ecosystem present today. I mean, you look at some of the sites up in upstate New York, right, that are manufacturing or getting ready to manufacture state-of-the-art technologies. I mean, it's something that doesn't happen without a CHIPS initiative. And then it'll bring things like restaurants, homes, and other things, right? It'll be a magnet for many of those items. So now after you pivot off of the microelectronics piece, you take yet another interesting turn here, more on the Department of Energy side, correct?
Well, I at the same time I was doing the AOA, I led a $200 million a year program in R&D for strategic systems. But then, as what happens a lot of times in military careers, is you go to school for a technical degree and then they send you to program management. And I went back into the Department of Defense in an Air Force job, led 2 ACAT-1 programs. So those are the largest acquisition programs in the DoD. There's about 100 every year. I was leading 2 at the same time.
Can you describe what an ACAT-1 is?
The actual numbers I forget, but they're multi-billion-dollar programs or very high interest. Yeah. So there's ACAT 1 through 3. It kind of it describes the level and approvals that you need to proceed in the acquisition.
So it's almost like the crown jewel investments.
Yeah, is the biggest investments. Yep, in DoD, and then towards the end of that tour, I was the chief scientist for the largest acquisition program currently in development in the DoD. It's now $140 billion.
You're over in Utah for that one, right?
Correct. Yeah, Hill Air Force Base. Yeah, it was amazing. It was that system is much more complex than just the missile. And I think I didn't truly appreciate how complex it was until I really looked at the architecture of the current system and how they were going to have to not just develop the next system, but actually deploy it in the fields in northern states with difficult workforce requirements, getting people up there with clearances, and it's going to be a huge challenge.
Well, this leverages a lot of your lessons learned on the political side, right? Now you're dealing with NORAD, Northcom, Stratcom. I mean, it's yet another set of politics that are heavily saturated in specific beliefs on how things have to be done, right? And so you have in I guess in parallel, right? You're working this AOA piece with the people that are very passionate about what has to be done. I mean, I lived through this, right? And we were part of the story of your AOA at DMEA. But there was a passion level at all of those sites. I have to imagine it was the same thing on the Hill Air Force Base related.
Yeah. I think the best lesson I learned early on was if you come to a a difficult road in your discussions, fall back to what you agree on. So if there's a disagreement, take a step back and say, what do we agree on? And that can be something as simple as where we're going to go for dinner. And then you build from there. Yeah. And I think that's a good analogy for the country right now. And in a lot of ways, I wish that we would just sit down and say, what do we agree on? Not what do we disagree on, but what do we agree on? And I think we'd find that we agree on a lot of things.
Yeah, because it becomes a pattern, right? You start just getting used to saying no, right? Just like you can get used to saying yes. And it all depends on the direction on how you do. That's an interesting perspective there. Now you've led this humongous ACAT 1 program, right? And you take a couple more I guess details within the Air Force prior to where you're at today, correct?
I took another detour and I went over to the UK. I've always had a fascination in geopolitics and international diplomacy. I had an early taste of this when I was at Hanscom Air Force Base, my first tour. I mediated some discussions between some ex-Soviet countries, so Azerbaijan and Armenia and Ukraine and Moldova. And that kind of got me really interested in geopolitics and how to resolve disputes. And when this UK job came up, not that we have a dispute with them, but I really wanted to flex my diplomacy muscle. And I went over there, worked with the Ministry of Defense on some programs together. I also, interestingly, got pulled into the fusion energy space at that time. I was close to Oxford, and that's where a lot of the fusion energy development work is going on there. And we had some senior leaders from the Pentagon come over and want to talk about fusion energy.
So yeah, describe what do you mean by fusion energy?
Yeah, fusion energy, taking two very light elements and making them one larger element. So that's the opposite of fission. Fission is taking one large element, usually uranium, plutonium, very, very heavy elements, splitting them into two or more. And those two or more usually are very radioactive. But fusion, on the other hand, is taking two really light elements, usually isotopes of hydrogen, but can also be helium and slightly larger isotopes.
So the beginning of the periodic table.
Yeah, beginning of the periodic table, yeah. And slamming them together however you want to do that, whether it's using X-rays or lasers or magnetic fields, smushing those together and making them one. And it's been tough. I mean, obviously, it's been worked on the first neutrons from a fusion reaction were detected in 1933. So we've been doing fusion for a long, long time, but we have never developed a net energy fusion device.
So let me ask the question for those that don't follow the science, quite specifically. Okay, so you're slamming these guys together, right? Who cares? Why would that make a difference in someone's life? Why is that such a big deal?
We need on-demand, zero carbon source of energy throughout the world. I mean, that's the basic promise of fusion. Fission also does fill that need, but it has all the negative attributes of highly radioactive spent fuel, safety concerns, whether they're real or perceived. It's very expensive to bring those online and very costly. Fusion, on the other hand, has no radioactive waste from the fuel. It does, depending on the fuel source, it does what they call activate the surrounding material. So the neutrons from the reaction go into the outer material of the vacuum chamber, and you can get small radioactivity from that. But it's of the level that you can set it aside for 10, 20 years, and then you can throw it away in a normal dump.
So there's a disposal process.
There's a disposal process, but it is nothing like fission energy.
Okay, and underneath this, the idea is that this will be a alternative energy source that is going to help, I guess, humankind as they go forward, as we harness this capability during its advancements, I guess, down the road, right?
I think this is the energy source for at least the next 2 centuries. Wind and solar will have a place, no doubt, and hydro will have a place, no doubt, and I'm big proponents where they make sense. But fusion will be a big part of that depending on the location and those other energy sources.
So this is where you got a taste of that.
Part of my PhD dissertation was in fusion. And I started watching the fusion energy sector, the private fusion energy sector, about 2010. And at that time, it was about 2013, and the Air Force was looking to downsize. I got a hold of a fusion company CEO, and I talked to him on the phone, and I said, hey, I'm really interested in fusion energy. And he said, don't quit your day job. Don't get into this right now. And I thought, you're in the space.
Yeah.
You should be a proponent for it.
Yeah, he should be all gung-ho for this, right?
Right.
Especially someone from the government calling and saying, I'm interested. You would think that, hey, you know what? Let's get you to dinner. Let's have a discussion. But he said, no, not yet.
No, yeah, the grants, it was a lot of grants, government grants, and those were drying up as the days of sequestration. Federal budgets in the U.S. were decreasing, and in Europe too. So it was very difficult. Fast forward to about 2020, 2021, when I start looking at fusion again, I call him up and he said, now's the time.
So you guys kept the relationship.
Absolutely.
Enough?
Yeah, absolutely. Yeah. And we still talk almost every week to this day. Yeah, he's been a big mentor of mine in that area.
That's incredible. Yeah. So then you left the UK, came back, and I think this is where our paths crossed again. And you said, look, I think this is going to be my last tour within the Air Force, and I'm looking to, kind of follow some of the passions that I have, right? And go pursue those said passions. Obviously, fusion's one of the big ones, right?
I was for the long time, I had this entrepreneurial itch. I kind of satisfied that a little bit by having a commercial real estate company on the side, buying office and retail spaces. And that got me far enough along, but at a certain point, I really wanted to stretch my legs and start my own business. And fusion made the perfect sense.
Outstanding. Yeah, and I've seen, just at this conference alone, your name has popped up on all fusion discussions, right? We ran in, I'll put up a couple plugs in for the companies we chatted with, Fuse being one of them, talking about how influential you've been to some of the stuff that they're building out there and the such. So when we talk about this being the next generation energy source, how far do you think we are from something like that?
Everything in life is a probability. So I'm a Monte Carlo simulator. And I don't think anything is deterministic. I think there's a whole range of future outcomes that can happen. So for me, what I like to look at is what are the left and right boundaries of my probability density function. And on the leftmost boundary is stated public agreement between Helion and Microsoft for electrons on the grid in 2028, 2029. And then on the right-hand side, you have a UK program called STEP, the Spherical Tokamak for Energy Production. And that is a well peer-reviewed timeline. It's a well-understood platform. So I think that's a conservative date in my mind. And there's a number of other countries pushing for about 2040 for a publicly funded effort. 2028, 2040 is my boundary. Most people in the industry would say in the early 2030s. I'm kind of with them. 2033, if I were to put my money on 1 year, I think we're going to have, and I'm not going to say it'll be on the grid, and I'm not going to say it'll be a whole integrated system with the tritium breeding and all the hooked up to turbines and all that stuff. But we will have a design by 2030, I believe, that will show net energy after taking into account all of the inefficiencies with everything else in the system that you would need to put it on the grid, which I think is, that is going to be such a mankind changing accomplishment.
So let me see if I understood what you said. In the 2030 time frame, that this is no longer going to be an R&D project. This is going to be something that's actually contributing back to its location for an energy source. Do I have that correct?
I think it'll be demonstrated. It may not be actually producing electricity, but we'll have a demonstrated design that we can build on the, to put something on the grid.
And just like any technology evolution, right? You look back at AI at its first, steps of things. Where we're at today versus where we were 5 years ago, right? The first demonstrator of AI-related stuff. It was all over the place. It was very hard to, get something that even looked realistic. Today, sometimes, you look online and you can't even tell if a picture's, someone, jumping into a pool or if it's real or fake. It's the technology just continues to advance. So you believe that that's kind of the progression that we're on here.
Yeah, absolutely. And the reason that it's now, I think one is the enabling technologies have come to a maturity level and a cost that can be incorporated in fusion devices. Specifically, high temperature superconducting tape has
what is that?
Yeah, so it's a tape. Most of the people use Rebco, and that's rare earth based tape. And if you cool it to liquid nitrogen temperatures, you can produce superconductivity, which means you can flow a current through there without any heat or resistive losses. So that allows you to go to much higher magnetic fields, which makes the fusion reactions possible.
Make sure I'm tracking this. I mean, it is the superconducting version of duct tape. And you just kind of put it on there and you super cool it down, but then it has the ability to help the fusion, reaction.
Yeah, and it comes in, it looks like tape, and you wind it into, sometimes they call pancakes, and they make a big magnet out of it. But that, not just 10 years ago, you could only get small little samples like that. And within the last 5 years, because of fusion, you can get thousands of kilometers of tape at a price that makes a fusion device economical.
Are we reliant on anyone for that, or is that U.S.?
Yes, that's a great question. The U.S. right now has the lead, but it could be quickly surpassed. And that is one of the critical underlying technologies that we should invest in from a government perspective. Right now, there are 3 companies in the U.S., 2 companies in Japan, and 1 company in China. And we really need to build out that ecosystem. It's not just important for fusion. So this is a great example where fusion is already making a difference. Fusion has caused the HTS manufacturers to grow and to decrease their costs. Without fusion, it never would have happened. And now we can use them in national defense products. So you can use them in directed energy weapons. You can use them in electric motors. You can use them in degaussing systems for Navy ships. You can use them in power distribution on Navy ships. Like it's transformational. It's going to be everywhere. And fusion already made a difference.
So it sounds like fusion has a lot of similar technology overlaps like microelectronics. It's an enabling technology, right? An example I like to use all the time is microelectronics is required by hypersonics to, achieve its mission. But you don't need hypersonics to manufacture microelectronics. So it sounds like fusion's kind of in the same boat, right? It's an enabling technology for all of these different types of items that now have impacts for the spectrum of things that you were just describing, right?
And other systems like nuclear effects platforms. So these fusion devices produce neutrons and X-rays that we can use for defense testing. And that's been a huge shift in this community where you have private companies getting private funding and developing new test capabilities in really short timelines and delivering them to the DoD for use. I mean, I've never seen that in my lifetime. And whereas, like, if we needed a new platform in the DoD, it would take probably 5 years to go from starting to look at it to convincing people you need it to getting in the budget and getting money, into your hands to do something about it. At least 5 years. I mean, that's being generous. And then another maybe 5 years to do a cost plus fixed fee contract to get something developed and produced. And then you have the gyrations in between of continuous resolutions and budget cuts and all the reporting that the government requires along the way. Now, a company can go and get private money in less than a year, can develop these capabilities in less than a year, and it's there for DoD now. And they're using that as a basis to generate revenue on the path to fusion energy and to work on some of the underlying components that will be needed for fusion energy. So in the end, there's a payoff, a big payoff for the investors, but in the near term, defense can take advantage of it.
Yeah, well, I mean, and I think their investments are going to help be an enabling function for a lot of these different advancements, right? Defense Department typically is one of those that helps to, push along technologies. And once it starts getting its traction, industry also all of a sudden kind of carries the weight, right? Same thing with the fusion industry as well.
Yeah, absolutely. We have to give credit to the huge public investments for the last 80 years in fusion. And in particular, obviously, after World War II. But the National Ignition Facility at Lawrence Livermore National Labs has been huge. The Z Machine at General Atomics has D3D. The ITER program over in Europe, although it's not online, it has funded a lot of efforts that are enabling these private companies to succeed. Now it is the time where private companies are taking over the mantle to develop this even further.
What do you think the big hurdle is going to be? Because right now what I'm hearing is hey, we're on a streamlined trajectory here, but there's always challenges, right? What's the big hurdle in the fusion industry right now?
So pending any technical challenge in the fusion approach itself. So right now, the ones that I follow, I don't know of any technical hurdle that is insurmountable, but you never know you never know until you start really ramping up the energy and the density and the temperatures.
Is there any like regulatory challenges here?
We would have said that a couple of years, but the US and the UK have been very open-minded, and they are now being regulated like accelerators, not like fission reactors. So we don't believe regulations are going to be a challenge. Obviously, getting anything on the grid takes a long time, and a lot of it is for good reason. You need to maintain the stability of the grid, so that'll be timely. If I were to think about like what is being underinvested in fusion, there's enough fusion approaches being adequately funded that I think we're going to get at least one to the finish line from the specific fusion approach. But now it's the ancillary equipment that needs to be worked on, and a lot of these enabling components and the supply chain. So a good example of that is the tritium systems. Most fusion approaches use deuterium and tritium, so those are isotopes of hydrogen. Deuterium you can get in seawater. Tritium you have to breed, and the way that you breed that in fusion reactions is that you get a neutron off of the deuterium tritium. That neutron goes into a lithium blanket. The lithium then produces tritium that you can then put back into the system. But tritium is not used in many applications. It has a decently short half-life.
Yeah, I was going to say the stability of it must be something.
Right, and it's a hydrogen isotope, so it's a small element. It can permeate into a lot of things and leak. And it's not insurmountable, but it is a challenge. There are already tritium systems that are being run. Shine has a deuterium tritium reactor that they use for medical isotope production. So it can be done. But doing that in a lithium blanket that also captures the heat from the byproducts, then that has to go to a heat exchanger, and then the heat exchanger goes, the water from the heat exchanger goes into a turbine, and then it turns a turbine, and then you get electricity. That whole system hasn't been demonstrated. That's going to be a big challenge. Scaling up, I really think scaling up is going to be who wins, meaning there's going to be a first of a kind, and I think the first of a kind is going to be in the US, if I were to bet. But the winner's not going to be the first one. The winner's going to be who can deploy as fast as they can globally at the lowest cost. And that's a supply chain challenge. And that's where we aren't focusing right now. Yeah, there needs to be more standards written in how you produce these components. Common performance parameters, saying like pulse power switches. How many kilovolts, how many amps do you want in this pulse power switch? Right now, none of the companies are communicating that openly, and they're probably all different. So it's hard for one company to stand up a line based on one specific need at one specific fusion company when they don't know if that one's going to actually make it to the end.
Interesting. So you're thinking that risk gets reduced in this whole thing, not so much as, first one across the finish line, but how many races you win, right? So if you're able to deploy this in Cleveland, in Omaha, in Sacramento, all these different cities, the person that's able to expand the fastest has the highest probability of success.
Absolutely. Singapore, globally, we need to win this race. Yep. And everybody's going to want one. And I'll also say, once that first one is successful, you're going to see a lot of copycats very quickly, I think.
Yeah, well, because all the heavy lifting has been done, right?
It's been done. And even if there's patents, not every country will follow our patent law.
Or
right?
respect them, right? They're just going to go ahead and...
So we need to be fast is the point, and we need to be working that supply chain. Now, and the way that we're working it, going into kind of what I'm doing now, This also fits into the onshoring manufacturing theme that the current administration is pushing, and that I very strongly believe in. We need to consolidate our manufacturing base to some extent. We need to, in particular for fusion, we need to look at companies that are producing products for other industries already. What can we do to position those products to maybe do a little bit of R&D to align those to what fusion companies need? I'm not sure that the supply chain in fusion is going to be solved by a lot of venture capital. I think if we were to look back, let's say 20 years from now, and it's successful, I think it's going to be a lot of small business owners with great business acumen, doing just common sense things to keep their company profitable, but then to align to future demand and ramp when you need. And that's where consolidation comes in.
So you think there's an avenue for micro investments into this, not looking for one person to, carry the weight of the investments like you see with, venture capitalists or private equity. You see this being a collection of folks all putting in their small pieces to help this, dream become a reality.
Yeah. And those companies may not be, they may stay a loosely knit organization. They may not be consolidated from a legal standpoint or from a business standpoint. But there is so much opportunity right now in investment in manufacturing in the U.S. Small business manufacturers are ripe for investment and focus and scaling. I don't think there's a better place to invest right now, but we don't have as many VCs. We don't have as many private equity groups. We just don't see it.
How does one get in there? So I have my checkbook and I'm like, hey, Greg, this sounds great. You sold me on it. I mean, you don't really go on to, your Robinhood account and say, okay, let me look at Fusion and then do an how do people on the outside get involved in this?
I'll start from the public side. The only public company that I know that you can invest in that has that's related to fusion, and I'm not recommending any company, but American Superconductor is a publicly traded company, produces HDST. Everything else is private. And if you go to the fusion investors conferences that I go to, all of the fusion companies are there, and a lot of the VCs that are interested are there. So Fusion X Invest, if you're interested, definitely take a look on the web. They have about 4 meetings a year between Europe, US, and Asia. That's garnered most of the attention in the space, which is specific fusion approaches. And those are very interesting and very important, but I don't see the attention on the supply chain. I mean, there's a very limited amount of investors in that space. And it's very difficult to communicate like what you're doing. I think just in general, investing in manufacturing companies is more challenging than software companies because you have a lot of high overhead, a lot of equipment. The timelines for payback are much longer.
And it's a complex science.
And it's very complex, very complex.
I mean, going in and describing what you just described today on a 30-second elevator speech for someone to, either be an advocate for, an investor for, help write policy for. I mean, there's a whole spectrum of different things. It's a challenge. I mean, not everyone is very well versed in, periodic table, half-lives, all those different stuff that we described. So I think that as people start to become more accustomed to it, it's the same barrier that we cross with other technologies, right? I mean, look at the cyber world right now. The cyber world, you flash back to the 90s and a lot of the topics that were there were very foreign to people. Now today, it's on the tip of people's tongues, right? So I think that as this progresses down towards the 2030 timeframe, it'll be one of those things by repeatability. People will have heard this. Oh, okay. I see what you're talking about, fusion. I see where this is going. And now they can start connecting the dots in all of these different areas, right?
Yeah. And there'll be examples of companies that have been invested in and that have been successful. I mean, I really think manufacturing as a service, I'm really waiting for that theme to become much more popular. There are some investors that are in that space, but it's not a large amount. So manufacturing as a service, meaning you're a manufacturer that makes components for other people. And those components are, particularly in the US, would be, highly complex, different materials, maybe large components. And that's just not as common of an investing theme.
So I'm going to circle back to something that you mentioned a few minutes ago, which was the White House, right? How has the influence been from, or I guess the perspective from the White House on fusion energy? Is this something that they are adopting as, hey, you know what, this is a good idea? Is there a hesitancy? I mean, most of the time, there's a lot of questions whenever new technologies come up to, different offices within the government, especially the White House. What's been the reaction that you've seen there?
From the Department of Energy leadership, it's been fantastic. Secretary Wright is a huge proponent for fusion, which was great to see. We don't know yet, like, what does that mean in the long term? How does that affect funding for public-private partnerships? How does that affect funding for public efforts like ITER over in Europe, or like D3D and at General Atomics, which is another tokamak, and then all the way down to like NSF funding for scientific research and all the other implications we just don't know yet.
Well, so as you're going forward, I mean, we covered a number of different things, right? Microelectronics, fusion, dairy farming. I mean, just a whole spectrum of stuff. What's next for Greg? I mean, you've done so many different things where you're impacting pretty critical portions of not only investments domestically, but also worldwide. I mean, we didn't even touch on some of the stuff that you're doing for, high energy, heavy ion, single event effect radiation test facilities, which is a whole nother segment we could get into. But what is next? Are you do you see yourself following this trajectory with fusion and seeing it to close out as being kind of the one of the pinnacle pieces of your career? Do you think that there's another passion you have? I guess what's next for Greg?
I view my life in 3 careers, and maybe that's not common, but I think I have 3 20-year careers. So my first 20 years, well, actually 22 years, was in the Air Force. And I did that, and that's recently closed. Now I'm in my second 20, and I'll talk about that in a moment. My last 20, I think it's advisory, mentoring, those types of jobs. So we'll leave that aside. That could be in a number of different areas. But this next 20, I want to build the largest fusion supply chain company in the world. And I want to deliver on-demand, carbon-free energy everywhere and bring manufacturing back to the U.S. in a way that we haven't seen since the end of World War II.
And you're seeing the adoption from countries like, Saudi, that has the line, right? Which is a self-sustained ecosystem, and a fusion-based type of approach would be perfect for that self-sustainment kind of piece. We talked about a lot of the domestic investment here. I mean, it looks like the human race is kind of moving in a direction where a carbon-free energy source is something that they know that there is a need for. They just don't know how and when it's going to happen. So that's an exciting piece, especially in this next period of time, which thankfully your 20-year second career here overlaps with your, prediction of the fusion stuff. So Greg, this was great, man. Thanks for coming onto the podcast here, and looking forward to, following you not only in your career, but continuing our friendship. So thanks, man.
Thanks, Dan. Appreciate it.